This is a tutorial on how to extract electricity from redox reactions and actually get some useful work out of the deal. Let's take, for example, this redox reaction here. We can think of it maybe also as a single replacement reaction where zinc metal reacts with some solution, some copper solution, maybe copper sulfate or something like that. I'm just writing a net ionic equation here. But so we have some copper ions floating around in solution, and let's say that the zinc metal is the one that gets oxidized. So it's going from 0 over on this reactant side to a +2 oxidation state, whereas the copper ions that are aqueous here floating around in solution become reduced to copper metal. Well, if we break this up into two half reactions, as we've done a few times before in other situations, we see that the oxidation half reaction, zinc metal breaks down to produce zinc ions in aqueous solution, and then in the process 2 electrons are given away. Okay, given away to what? Well, to the copper in the reduction half. So here's the reduction half reaction. We have soluble copper 2+ ions, aqueous, floating around. They're going to grab those 2 electrons given away by the zinc, and in the process the copper will be reduced to copper metal. It's going from a +2 oxidation number to a 0 oxidation number. So the oxidation number is reduced. Copper is reduced. Okay, well, that's all well and good, but if we just left it in the same container like that, the 2 electrons from the zinc would be transferred to the copper and would get used up, but no useful work. It would drive the reaction, but no useful work could be done, like producing electricity or anything. What if we, instead of keeping them both in the same container, what if we put them each in their own container? So if I have beaker number 1 with a zinc metal, so this is a zinc metal strip, let's say, and it's just bathed in a let's say a sulfate solution or something like that. So it's just water and some sulfate ions floating around in solution. Okay, let's take copper metal and put it in its own beaker, and inside the beaker, besides the copper strip, is another sulfate type of solution. Well, neither of these would react at this point because they are not connected. All we have is 2 isolated half reactions not communicating with each other. Okay? But what if we connect the 2? Not by mixing them together into the same beaker, but by attaching, let's say, an alligator lead here to the top of this zinc, a wire, let's say, external wire. Maybe we could put a light bulb or something in between, and attaching to the copper. So here's a little lamp. Alright, and then complete the circuit with maybe some moist paper towel containing some of these, some kind of an ionic solution, maybe some kind of a bridge across from here to here, maybe like a moist piece of paper towel or a tube filled with agar gel that also contains some kind of salty ionic material. Okay, so this will be our what's known as a salt bridge. What we've now made is what's called a Daniell cell. Okay? the basic idea is that instead of the electrons from the oxidation half reaction just directly being given to the reduction half, the electrons are going to be given to the reduction half by way of an external wire. In this case, maybe going through a lamp or something like that, and actually lighting up the lamp. Okay, well, let's see how that works. Now, we have our two separate half cells. Okay, and at the anode side, we don't need to get caught up on anode, but this is the anode side, and this would be the cathode side. At the zinc side, let's just call it that, zinc atoms undergo oxidation to form zinc 2+ ions, don't they? And so I can show that basically we get zinc metal converting to Zn2+. And those ions are soluble in water, and they're just floating around in solution. Notice that the zinc metal actually deteriorates as more and more of those zinc ions form. So this basically, the zinc metal over a period of time gets deteriorated or eaten up. Okay, well, what happens once the zinc ions are formed? 2 electrons are released. Those 2 electrons, for each one of these zinc atoms that forms a zinc 2+ ion, we have 2 electrons that build up in this metal. And so we get electrons building up in the zinc metal there. Okay? They eventually find their way over through the external circuit, through the wire, light up the lamp, or run the motor, or whatever would be there, and then eventually get over to the other side. Now those, of course, there are electrons all in that wire originally, so we don't have to wait for one electron over here to crawl its way over to the other side at a snail's pace. The electrons that are already over here in this copper wire will immediately go to the copper. And of course the copper, which is a reduction half reaction, it's going to say thank you very much. It's going to want to grab those electrons to form copper metal. Okay? So the copper ions that are in this solution here, copper ions that are floating around in this solution, we might have started out with copper 2 sulfate or something like that on this side. Maybe over on this side it was zinc sulfate. But anyway, there were copper 2 ions already in this solution to begin with. When they bounce into this copper metal here, with all of these electrons piling in from the other side, they're going to grab those 2 electrons to form copper metal. And as the copper metal gets formed, the copper strip is going to get bigger and bigger and bigger with more copper. So we get a bigger accumulation of copper here, whereas on the other side we get the zinc strip deteriorating away. Okay, so notice the buildup of the copper metal on this side and the breakdown of the zinc metal on the left side. Okay, so you can see now that how batteries work. This is a simple electrochemical cell. It's not a battery as such, because a battery would be more than one of these electrochemical cells stacked together, and a stack of these is called a battery. Now each half cell reaction has a certain electrical potential, or known as a voltage, that can be looked up on a standard reduction potentials chart. Okay, let me show you an example of one of those charts right here. This is just definitely not an all-inclusive table. Okay, and these potentials have been found experimentally. Excuse me, light went off. Great automatic lights. Okay, and we can see here that these, by experimentation, were found at temperature of 25 degrees C, 101 kilopascals. That's basic sea level barometric pressure. Okay, and for a 1 molar concentrated solution of these things. Okay. Now this standard reduction potential table can be used to do a couple of things. For example, how much voltage is generated by this particular setup, this Daniell cell. Okay, that's one thing it can do. Okay, let's show how that works. So basically, we can look up. We see that copper 2 plus. I'll just put a dot next to it on this chart. Copper 2 plus grabs 2 electrons to form copper metal, and this is exactly what happened, huh? This is the reduction half. Now, since this table of values is written in terms of reduction, all of them are written in the form of reduction halves. We would have to flip it around for our oxidation half, which would be the zinc half, right? Okay, so if we look for zinc, we see that there's zinc 2 plus right up here. But it's showing it as a reduction half reaction. But we see up here that our half reaction for zinc was an oxidation half reaction. So what we need to do is flip that around. Zn arrow zinc 2 plus plus 2 electrons. If we flip that around, that means we also have to change the sign. So instead of a negative sign there, we need to put a positive sign. Okay? So what is the total voltage produced by that Daniell cell up there if we have these solutions being 1 molar concentration at 25 degrees and atmospheric pressure? Well, it would be this value here, 0.34 volts, plus 0.76 volts. So 0.76 volts plus 0.34 volts, and that gives us 1.10 volts total for our copper and zinc electrochemical cell. So that's one thing we can do. We can find how much voltage we'd expect given 2 different metals in these solutions. Okay? The other thing we can do is to predict whether a reaction will occur or not in that particular direction. Let's take, for example, this reaction here. Aluminum ions reacting with nickel metal. So this is aqueous here for the aluminum ions, reacting with solid nickel metal to produce nickel ions plus aluminum metal. Okay, is this going to proceed in that direction? Will it occur as written? Well, let's look up the voltages of the 2 half reactions. Okay, let's see. We have aluminum right here. I'll circle that. It's getting kind of cluttered up here. The aluminum ions, negative 1.68. So for that half reaction, Al plus 3 plus electrons gives plus 3 electrons, give aluminum metal, and the voltage is negative 1.68 volts. Now that's showing as a reduction as written on the table. Okay, now let's look for nickel. Do we have any that go from nickel to nickel 2 plus? We have a nickel 2 plus to a nickel. It shows it as a reduction. In my reaction here, it's showing that nickel's going from 0 to a plus 2, which means oxidation. So we would have to flip that around, wouldn't we, if we wanted to find the total voltage produced by this reaction. However, in this case, we want to see whether the reaction occurs at all in this direction. So anyway, we wouldn't flip it around. We would just leave it as such. We'd write nickel, or actually we would flip it around, nickel to produce nickel ions, 2 plus how many electrons? Okay, plus 2 electrons. And the voltage associated with that oxidation condition, we'd have to flip the sign. It would be a plus 0.26 volts. Now if we add the two together, a negative 1.68 volts and a plus 0.26 volts, we end up with negative 1.42 volts. Okay. Now, if you remember from the previous example, we had a positive 1.10 volt total. And I know from experience that that reaction of the Daniell cell with copper and zinc spontaneously occurs. We had a positive voltage. In this case, though, it's showing negative, isn't it? So what does that mean? Well, for a reaction to take place, there must be a positive voltage as determined by your reduction potential table. If it's negative, okay, no reaction will occur. Okay, so since negative, that means no reaction will occur. Must be positive, like the one we found for the previous example. Okay? So in summary then, we can make an electrochemical cell by splitting up the two half reactions. Okay? And routing the electrons given off by the oxidation half through an external circuit to get to the other side. Oh, before I close, what is the purpose of this salt bridge? Well, I guess you could just say it basically completes the circuit. Okay. Because, well, what happens? If we look here and use your imagination now, more and more zinc ions are building up in this solution as the zinc metal breaks down. Okay? Here we go again with the automatic lights. So this whole system becomes more positive. Well, if you have all these positive charges here building up, they're going to inhibit electron flow outward. They're going to try to hold on to those negatives, aren't they? So it's not good to have a big buildup of positive ions in the solution. So this salt bridge allows some of those positive ions to flow either into that salt bridge like that. Let's look at the other side. As copper ions from this solution are used up to form copper metal, it becomes more negative over on this side as those copper ions get used up. This becomes more negative. If this area here becomes more negative, that increased amount of negatives are going to repel any incoming electrons. So they're going to exert a push away to prevent more electrons from coming in. Okay, so if this is becoming more negative here, what happens if some of these sulfate ions start to diffuse through the salt bridge? Well, that's going to lessen the amount of negatives over here, isn't it? Those sulfates then would travel over to this side to help neutralize the positive charges that tend to be building up in this zinc solution. Therefore, it's going to kind of maintain each one of these beakers neutrality, isn't it? So that we don't have the electrons prevented from going through their external circuit. Remember, if positives build up here, they're going to attract those electrons and inhibit them from going to the external circuit. Remember, if this builds up more negative here because the copper ions are being used up, that's going to prevent incoming electrons from coming onto that copper. So to avoid that problem, we have this salt bridge here, so that negative ions, sulfate ions in this example, flow through the salt bridge to the zinc side, therefore neutralizing the positive charge in the solution here, and minimizing the amount of negative charge in this solution over here. Okay? Without that salt bridge, the total reaction will not take place. You need to have this in order for it to work. Thank you, everybody.